So a couple of just little logistical things so we're all on the same page here. Your homework is back. Those projectile motion tests, I know I told you I was going to get, I'm so close. They take a long time, those last questions, so I apologize. I'll get those to you tomorrow. Fingers crossed and all of that good stuff. I want to look at the schedule with you for Unit 3 so you can see where it's going and what we're doing. And then we'll start with the warm-up problem. We're going to jump into Unit 3 today. It's going to be great. So here you go. So this is just a copy and paste from Canvas so that I didn't have to pull Canvas up. So today is the 4th. Okay, we're going to start Unit 3, and we're going to go Monday, Tuesday, Wednesday, Thursday, Friday, Monday, and then we're going to take a Unit 4 assessment on Tuesday of next week. Okay, is that making sense to everybody? So that's officially our first of our finals days. So next Tuesday, we will take a Unit 4 assessment. This is a pretty short unit, and I will tell you, friends, that the content you'll see here is really just Newton's first and second law. But wait, Mr. Harper, we already did that. I know. It's just like another little twist in the same story. So that's important to know. And then next Wednesday, Thursday, Friday are going to be review days. And then the following Monday, the last day of the try, we are going to do a mini AP exam, just multiple choice, okay? AP questions graded on the AP scale, okay? And that will be on the 18th, and that will be our second final. So that'll be like our official finals, okay? Questions that you have for me about all of this? Go ahead.
Will the second, mini final go in as trimester 2?
So this thing right here will be the last thing in for trimester 1. Yes. And it will be cumulative over the entire try, right? Because we're building up. So second trimester, spoiler alert, the final will be over both first and second try. And then the final for third trimester, spoiler alert, will be over first, second, and third trimester. And it will also be before the AP exam. Okay, so we will get you there. That's my goal. That's my job. Yes.
Where do we turn in the admins?
I thought that it was that you could do it on Canvas. If you can't, if you need me to, just email it to me. Okay. That's easiest for me. Yeah. Okay. One other thing, just logistical thing for you. I forgot to put it up on here. On Friday, I had given you those multiple choice questions, those review questions from the AP website. And I just went on to look, and some of you have started it. Some of you have not finished it. Tony, I know that you had a hard time getting a hold of it, right? Like you aren't able to access it. Okay. Is there anybody else that was not able to access it besides Tony? Okay. I'm going to print one off for you, and I'll get it to you. Does that sound okay? I'll just get you a hard copy? Okay. If you did not yet finish that, will you finish that, I don't know, let's say by Wednesday? Is that doable? Okay, so put that on your list of things to do if you have not already done that, okay? Is the AP multiple choice questions online? We'll get it out and look at it. That's what I wanted to do. Yeah. Does that make sense? Yeah. All right, friends. Any other logistical questions before we jump in and do physics? Okay, here we go. I've got a warm-up problem for you. This comes from a ranking task, but it's not the ranking task part. I just want you to take a look at this to start your brain kind of thinking. It says a 10-kilogram box, you may want to call it a mystery box, although it's not actually labeled that way, is initially at rest and moves along a frictionless horizontal surface. A horizontal force to the right is applied to the box. It says the magnitude of the force changes as a function of time as shown. It's a little different than we've done before. So just to be very clear about what that says, it says that the force changes as a function of time as shown. All I'm asking you to do, I don't want you to do math. I don't want you to go in and dig and figure. I just want you to use some words to describe the motion of the box over the time interval from 0 to 10 seconds. Okay, I'm going to give you just a couple minutes to do that. Go ahead and just write something down on your paper. Okay, it can be in a corner. It can be on a back of a piece of paper. It doesn't have to be perfect, but give that a shot. Describe the motion of the box over the time interval from 0 to 10 seconds. Go ahead and get started. I just want to kind of get a sense of what you think is going to happen, what's happening to this box, the motion of the box over time for this interval. Can somebody get me started? What's going to happen? Bo, go ahead.
From 0 seconds to 2 seconds, it's going from rest and is accelerating.
Okay. So from 0 to 2 seconds, it starts at rest. So the initial velocity is 0. And you said that it's accelerating.
It's accelerating.
Okay. How do you know that it's accelerating?
Because the is going up in
Okay. So it's accelerating because the force is increasing, he says. Thoughts about this or about another section that you want to talk about? Sid, can I pick on you? What did you guys say back there?
So I said that the acceleration is increasing for the first little bit.
Okay, so you said not only that the box is accelerating, but what now?
The acceleration is increasing for the first 2 seconds. And then it's a constant acceleration.
Is increasing. Why is the acceleration increasing?
Because the force is increasing and uses kilograms, meters.
Does that kind of make sense? So the acceleration, we're just going to remind ourselves, is F net over m, right? And so not only is the box accelerating, he's saying the net force is changing, and because the net force is changing, the acceleration is changing. So it's getting faster. That's different. We haven't really talked about that before, right? But it's just kind of, that's what we're saying here. So not only is it accelerating, I agree, it's starting off at 0, it's accelerating, but it's accelerating faster, and the rate of acceleration is increasing. Yeah.
It's not called right.
It is called jerk. Yes. We're not going to get into all of those details. Yes. So the rate of change of the acceleration is the jerk, right? So the it's not like really mean person. It's like, oh my gosh, you're like, like literally you feel like a jerk. That's what we're talking about. Yeah. So as F increases, the acceleration itself also increases. Awesome. All right. So let's move on to the next section here. It looks like the next kind of area to talk about might be from, what do you think? Like from 2 over to 5? So from 2 seconds to 5 seconds? What can y'all tell me about what's happening between 2 and 5 seconds? Say that again. It has a constant acceleration. It's a little weird. Usually when we look at graphs, if we have like a horizontal line, it means something stays the same, right? And it does mean that the force stays the same, but we have to remember that if the force is the same, that box is accelerating. So that whole time it's getting faster and faster and faster, right? Just at the same rate now. Is that okay? What happens between 6 and 8 seconds? The acceleration, so between 5 and 8 seconds. TJ, was that you?
Yeah.
What did you say? So the acceleration is decreasing. Now, we kind of got a little bit off track here because that doesn't really tell me a lot about the motion. So what does that mean if the acceleration is decreasing?
It's going to be at a constant speed at 8 seconds. Like the acceleration is approaching
Speeding up at a slower rate.
Yeah, it's speeding up at a slower rate.
Speeding up at a slower rate. Yes.
It's going fast, slowly.
Faster, slower than it was before. Yes. Yeah. Yes, the rate of change. Yes. So it's speeding up. What did you say, Caden? That was nicely put. Speeding up
slower.
at
At a lower decreasing rate.
slower rate. Okay. And then between 8 and 10 seconds, what happens between 8 and 10 seconds? Constant speed. And how do we know that it's a constant speed? Because I heard somebody say something over here. Yeah. If F net equals 0, then that means the acceleration equals 0, which means that the change in velocity is 0. Is there any place in this story besides at time equals 0 when the box is not moving? No, it's moving, and it's moving faster, faster, faster. Where is it moving the fastest? At what time or at what interval is the box moving the fastest?
8 seconds. Yeah.
What do you think, Brady? Where's it moving the fastest?
At the end.
At the end. Why do you mean like at 10 seconds?
Yeah.
What do you say?
Because that's when it has all the acceleration under 2 rhythms.
Yeah, so we got a bunch of acceleration. There's a bunch of acceleration from 0 to 2, and then from 2 to 5, and then 5 to 8. Is it moving faster at 10 or at 9? Same speed, right? But it's moving as fast as it's going to move in this story, starting at 8 seconds and from 8 to 10 seconds. Even though this is at 0. Are you with me here? Okay. The reason I like this graph, you guys, is because it doesn't, like, at first glance, you might not think that that's true, right? If I just threw this graph at you and said, hey, when is this box not moving or moving the fastest? Your gut might not be to say between 8 and 10, but you have to dig in a little bit. You see what I'm saying? You have to kind of think about what this is graphing and what the purpose of that is. Morgan, are you okay? Do you need to, like, take care of anything, or is everything good? Okay, fantastic. So between 8 and 10 seconds, it's moving at a constant speed. Yeah? Yeah, go.
Because it's something that's slightly off topic, but
Go for it.
yeah, what would the displacement graph look like? Would it be a cubic and a quadratic? Or...
That's a really good question. So talk to me about where that question is coming from, or like where your idea of cubic and quadratic are coming from.
So it should be seconds over meters cubed, right? So that's obviously it should be a cubic, right?
Yeah. So the force, because remember, force is just F net over, or acceleration is F net over m. So an acceleration graph is going to look very similar to that, right? Just with a shifted constant because of the m. So your acceleration graph would go up, over, down, and over as well. And so if this is your acceleration graph, then your velocity graph is going to be it's going to be a quadratic, right? And then it's going to be linear, and then it's going to be a quadratic and linear. And so then your position graph would be cubic, quadratic, cubic.
So it just increases by 1 exponent.
Exactly, every time. Yep. Are we going to have to do that in here? No, not here. But understanding this is important. And knowing that force can change is important, right? But we would never have to go from this to a position graph. It's a good question. And your calculus teacher likes that question too, right? Yeah, for sure. But I'm not going to make you do that question. Fair? All right. Do you guys know, have you ever gone to a store and gone in to like look for, the example I always think of is toothpaste. And you go in and you know like exactly the box of toothpaste that you're looking for. And it's like, it's got green and it's got blue and whatever. And you look for it and then you're like looking around the shelf and you cannot find your toothpaste. And then you stand there for a while and then you're like, oh, it's just in a different box. You know what I'm saying? It says like, same great stuff, new look or whatever. Okay? That's what unit 3 is. New look, same great physics. Are you ready? Yeah. This is the definition of Miss Carbeling getting a little bit too goofy with that concept last night while I was getting things ready. So here you go. Just a few old shout outs to like back in the day, the Oreos, right? Yeah, same great taste. Yeah, yeah. Okay. There's my Crest toothpaste from like, I don't know, the 1960s or something like that, right? Yeah, yeah. So do you guys know who this guy is right down here? Yeah, not my favorite person. But he is famous for Newton's first and second law, right? He's famous for it. And he wrote it in this book. I think I probably told you that Isaac Newton, one of the reasons that I don't like him, there are a few. One of the reasons I don't like him is because he figured out a bunch of stuff and then he didn't want to tell anybody. And he liked to be like, I know something nobody else knows. And I'm like, that's just not very kind, right? But then he wrote this book called the Principia and it had all of this stuff in it. And it had all of this and it just kind of like rocked the science world. And one of the things that he wrote in that was what we now call Newton's first and second law. Okay? So I'm going to write down for you the way that it looks in his book. Are you ready? Here it comes. You got to write this down too. Newton's first and second law. Here it is. You're like, I know this. I know you do. Because we did this last unit, right? So here's the law. Here's the law. There it is right there. That's Newton's first and second law. That's how it's written in the book. Is that how it looks to you? Is that how we've seen it in the past? No. You're like, you're lying, lies, right? But all it is, friends, same great physics, new look, right? This is the way he published it. In fact, there was a line right before it. I didn't put it in there because it would look really scary. It looks like this. Are you ready? Yeah, because there's a new letter in there. Yeah, the letter P. Does anybody know what the letter P stands for? I'll tell you. Momentum. Have you heard the word momentum before? Yeah, you've heard the word momentum before, probably. Probably you have. My first goal for you is to prove to you that this is really just Newton's first and second law in the way that you know it. Newton's first and second law in the way that you know it, we already wrote down. We wrote that down earlier when we were doing the graph. In what way do you know Newton's first and second law? How do you write it down? It starts with an A. A is equal to F net over mass, right? Okay. So we're just going to take a look real quick and make sure that I'm not trying to pull your leg and not trying to mess with your head and all of that sort of stuff because that's not my job, okay? My goal is to show you that this is the same as this. Can you believe it? Yeah? So you're like, yeah, of course, duh. Yeah. What's A? Acceleration, which is? Change of velocity over time. Okay, so let's just get it over time, shall we? So we're going to divide by delta t here. Divide by delta t here. Oh, look at that. That's acceleration. See ya. Okay. And then I'm just going to, I don't know, maybe like divide by mass. We okay there? And so really we've got A is equal to F over M, net force divided by mass. This is the way we know and love it. This is the way Mr. Isaac Newton wrote it down. That's really all of Unit 3 right there. Ready? I don't have a test written. I'll give it to you tomorrow, though. No. I mean, is there a little bit more to it? Probably a little bit, but it's all just in the details. This is it right here. This thing right here, so this is what we call Newton's first and second law, the one in the pink box, right? This is what we call, it has a big fancy name. Are you ready? Yeah, here it comes. I'm going to write it down. And I'll just write it wide over here. That's perfect. I'm going to put it right here. Big fancy name. And you know if it has a big fancy name, it's got to be important. Here it comes. It's called the impulse momentum theorem. It's called a theorem. It's got to be good, right? Yeah. The other theorems that you know you love. Yeah. What other theorems do you love? The fundamental theorem of algebra? The fundamental theorem of calculus? The theorem of Pythagoras? I mean, there are lots of them out there, right? And they're all pretty dear and near to our hearts. This one's another one that's going to go in there. Okay? we need to define a couple things. I'm going to write it right over here again. Delta P is equal to F delta T. Delta P means change in momentum. So if delta P means change in momentum, then P probably stands for mass times change in velocity. That's kind of what I'm thinking. Well, so delta P equals mass times change in velocity. And regular plain old P, momentum, is equal to mass times velocity. An object has momentum if it has what two things? Mass and velocity. Whoa! Not trying to mess with your head, right? If something has momentum, it has mass and velocity. So question for you. Which has more momentum? An elephant standing still or a little rock that's rolling along a road? The rock. Even though the elephant, as soon as the elephant starts moving, then it probably is going to have more momentum. You with me there? But if the elephant is standing still, even if the elephant has gigantic amounts of mass, if its velocity is 0, how much momentum does it have? 0. Okay? A little tiny rock that's got just almost no mass, if it's moving, has got some momentum. Yeah. That's the momentum part. That's half of it. That's this part. Then there's this other part called the impulse. Have you guys ever heard the word impulse before? In what context have you heard the word impulse before? What did you say? Impulse control. What does that mean? If you don't have very good impulse control, what does that mean? You're impulsive. Okay, now we're just like circularly defining things. What does it mean if you, yeah? You do something in the moment because you feel like it, right? Yeah. So today's lesson is really all about marketing. Okay? 2 things about marketing. The first one was the new boxes. The second one goes to my experience, your experience probably, okay? Wherever you like to shop, you go in with a list of things. You need to get 4 things, right? I need to get toothpaste, and I need to get Oreos, and I need to get milk. And then you got those things in your little cart, and you're walking up to the thing, and then wherever you like to shop, whether it's Target or Walmart or Walgreens or Hy-Vee or Fairway, I don't care. But you walk up, and what do they have right next to the register? Candy and gum and chapstick and batteries and all of these things that were not on your list. Are you with me? They were not on your list. But inside your basket, what do you end up with? Candy and gum and chapstick and all of those things that you did not need. Okay? You had some momentum because you have mass, right? And you were moving towards that cash register, right? To go pay for your Oreos and your toothpaste and what was the other thing? Milk. That's right. The other thing that I needed was milk. Right. Okay, so I got all those things. I'm walking. And what happens to me? I start walking this way to go get the candy and the gum and the chapstick. Like all that silly, goofy stuff. Right? Those marketing people, they know. They know that those are the things you want. Those are called impulse purchases. Did you know this? Yeah. Impulse purchases. Those things that you didn't plan to get. Right? Those things that you didn't plan. But your momentum changed. And as a result, you have $25 worth of stuff that you didn't intend to buy. Or whatever. Maybe that's a little bit of an exaggeration. Depends on how many things of chapstick you decided to get, right? Yeah. Impulse is often just labeled F delta T. It often doesn't use a letter, but I also know that a lot of physics students really like to have a letter associated with it. So I will tell you that in some textbooks, for impulse, they use the letter J. No, can't use I because that's for current. Sorry. And little I is like, imaginary number stuff. So yeah. J is impulse, and J is equal to F delta T, a force acting over a time. There's a lot of chatting, and it's really distracting to me. So please, like if you have a question, let me know. Okay, but otherwise, J, this impulse business, I don't even think it's that way in your book, but just again, some people like letters. Okay, is equal to F delta T, a force acting over a time. And the impulse momentum theorem says that a force acting over a time will cause a change in momentum. An object is going to change its velocity because of a force acting over a time. So it could be a really, really big force acting over a really, really short time. Okay? That's what we think of a lot of times when we think of things changing direction. But sometimes it's a very, very small force acting over a really, really long amount of time. You can get the same change in momentum doing that as well. Okay? How are we doing? Easy? This is not hard stuff. We got this. All right, we're going to take a look at a couple of questions. Because I think that's all I need to tell you about that. I think that's it. Here we go. All right, here we go. Speaking of, we've got, let me make that like the right size for you. Identical boxes filled with different objects are all initially at rest. A horizontal force is applied for 10 seconds, and the boxes move across the floor. The mass of the box with its contents and the net force acting on the box while the horizontal force is applied are given in each figure. It says, rank the magnitude of the change in momentum during the 10-second interval for each box. It can be done. Make it happen. All right, my friends, show me some boards. Help me out. What you got? Okay, so I see D, A, B, C.
You're frozen.
Oh, I'm frozen, so you can't see my orange letters. Chris, what are you doing, dude? Peer pressure?
No, I looked at theirs, then I looked at it, and now I found it myself.
All right, so I don't completely buy what you just said. So talk to me, my friends, about why you think that might be a right answer.
Okay, so.
Says the guy who just changed his mind.
No, I told Josh to write the wrong thing.
Were you trying to throw him under the bus or what?
Myself in telling him under the bus.
Okay.
So it's like this because
It's like this.
The formula of
I will look at the formula. What does the formula say?
that m delta v equals f delta t, and so delta t is just zero because it's irrelevant because it's the same for all of them. So we can just throw that away.
Okay.
And so then it's m delta v equals f. And delta v is acceleration, so it's a mass times acceleration equals change of velocity acceleration.
Over time. Change of velocity over time.
This is just a one-time change in the momentum equation.
What?
Is delta v not over time?
That is not over time. It's just delta v. M delta v is change in momentum. Are you changing your story again?
Hmm? It's
Talk to me, friends. I feel like we're not quite there yet. Impulse momentum theorem says that change in momentum is equal to force times change in time, right? Impulse, momentum, whee! So you want to do acceleration, right? That's what I feel like it's like, I want acceleration. Is there anything about acceleration in this problem? I mean, one could do this problem with acceleration, right? But I'm trying to give you the new improved box, right? The shiny new box with the glitter on the outside as opposed to the old dull yucky box, right? Impulse momentum theorem. What is it wanting to know? Change in momentum, right? That's all they want to know. The hardest thing in this chapter, the hardest thing in this unit is to make sure you don't overthink stuff. Okay? All that they're asking in this question is for the change in momentum. And the change in momentum is force times time. That's all it is.
The two mistakes I made canceled out because I thought that by acceleration it would have canceled out anyway, so I got the same thing as I would have if I did it that way. So we're gonna count myself as correct.
Today, we're lucky. We have to be careful about that. We don't want to guarantee that. So
the order of the forces.
I don't need anything.
Oh, you're just coming to say hi? Cool. You're always welcome. So the time is always the same.
Yeah.
So the force, the bigger the force, what? The bigger change in the momentum, right?
Which was my logic in looking at theirs, realizing, oh, C is bigger. Yeah, it wasn't just pure pressure. I did actually.
Okay. So I want to make sure because there were a lot of people that had this written down, but it's always a little, as a teacher, it's always a little nerve-wracking because I'm getting 4 brains or 3 brains on one board, and I want to make sure that everybody's brain is here. Are we okay with this? Is that making sense? Okay. Cool. Awesome. Not just one brain. I want all the brains right there. Woo! All right. Let me give you another one. Oh, yeah. Let's do it. Here we go. Hey, you've seen this graph. Hey, this is where it came from. All right. So now that you know a few more things, this is everything right here and below is where that problem, the warm-up problem came from. So the 10 kilogram box initially at rest, blah, 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 you know the story. It says to rank the impulse applied to the box by the force during each 2-second interval indicated below. Okay? I'm going to let you think for a few minutes. Impulse is force times time. Ooh, interesting. Is that how you're feeling? Okay, so here's the push that I would give you, and that is that we just defined this new crazy thing, right? Which I am frozen, so you can't see that I'm writing. And the new crazy thing that we defined is impulse, J, right? This thing called impulse, which is force times time. And so usually we think about a force that's constant and a time that's changing, but really there's nothing to say that one of them has to be constant. So anytime you want to calculate a force, or excuse me, an impulse, you're just going to do the force times the time. Can you see that on the board here? Can you see that in the graph? How would you find, let's look at from 2 to 4. Let's look at B. From 2 to 4 seconds. From 2 seconds to 4 seconds, the force is 3 newtons. How would you find the impulse? Let's do the math. A force of 3 newtons over 2 seconds. So 3 newtons times 2 seconds is an impulse of how much? 6 Newton seconds. Is that okay? It's Newton seconds. It's not J. J is the variable. Yes. The units for impulse is Newton seconds. There's nothing gorgeous about it, and there's nothing prettier. It's just Newton seconds. Newton seconds. What's the impulse between 8 and 10? Well, it's a force of 0 for 2 seconds. 0 times 2 is 0. Okay, can you do the other 2? Okay, or the other 3 or whatever? Do them. Go. And maybe you don't need numbers exactly, because all you need to do is calculate to rank. Yeah. Are we looking at slope here? Yeah, you're finding area. Yeah. So this is, go ahead. So what does the area, so let's write this down. The area of or the area between the axis, between the curve and axis for a force versus time graph is the what, friends? Is the what? The area is the, what are we looking for? The impulse. So if you look at each of those little slices, there's one, there's another, there's a third. Which one has the biggest area? 2 to 4? Which one's next? C? Which one's next? Yeah, then what? And then E. All right, friends. Have an awesome Monday. I will see you tomorrow. We'll keep cruising.